up.
And we'll go.
Oh, there we go. All right. Well, welcome, guys. This is PRV University. Hopefully everyone's in the right place. So we're going to learn everything and more than you ever wanted to know about pressure relief valve. So the acronym PRV is for pressure relief valves, also known as safety valves, right? Safety relief valves, but they're basically safety devices, pressure relief devices that are protecting your system, right? So we're going to cover everything, basics of how these, the most common type of devices, how they operate, the design elements in them and how they function, how they meet the requirements of the application. So like I said, we're going to get into some pretty good detail. This is a school we teach in our facility in Stafford, Texas, where we manufacture these, and we do like a whole week-long training. And we're condensing that into 4 hours. So it is a 4-hour presentation. So we're cramming a lot of information, and nothing better than a 4-hour presentation right after lunch, right? So we'll try to keep this lively, but feel free. This is a small group, so any questions, feel free to ask those, and we can make sure we address everything. So my name is Warren Booth. I am the area growth manager for the PRV and tank products. So I'm actually based in. So for Emerson, we have a group called pressure management, handle everything that does with managing pressure. So regulators, pressure relief devices, those kind of things. So our headquarters is in McKinney, Texas, just north of Dallas. That's where I reside. But the Stafford, Texas, down in Houston, that's where our Anderson, Greenwood, Crosby products, some other pressure relief brands are made. And then in Tulsa, Oklahoma is where our Anardo and Varick tank protection type products that will also go over here today. That's where they manufacture those. Okay. So I am area growth manager, kind of a regional role. I cover the Northeast US, Eastern and Atlantic Canada, and we have a whole swath down here in Southwest, like up in North Texas, Oklahoma, New Mexico. And I'll let you introduce himself. He's going to be teaching.
Yeah, so good afternoon, everyone. My name's Dean Morris. I'm actually Warren's counterpart, but I'm in the Southeast, so I cover Louisiana to Virginia. So I've been with Anderson Greenwood for 32 years. So I work for the Stafford manufacturing plant because he works for the headquarters up in McKinney. So when you think about pressure management, we always think safety. So hopefully you get some good information on this. Keep it up.
Yeah. So like I said, I'll be going into some great details. I'll go slow, depending on your experience. Maybe you've seen these things, you don't really know how they operate. It's kind of important to really understand how they operate, how they meet the requirements. They'll lay the foundation for the stuff we'll talk about later when we talk about monitoring the devices and trying to see exactly how much you're relieving, etc. Okay. So I'll start, like I said, group 1. I'll talk about just kind of an overview, basically, of what is overpressure protection, the requirements, different applications. And then we'll get into some specific, the most common type of pressure relief devices. So pressure relief devices could be a wide range, right? Go across things like what they call rupture disc or like a reclosing type valve, which is mainly what we'll talk about. So a direct spring pressure relief valve. And then Dean will cover pilot operated pressure relief valves, and then he'll go into safety selector valves. Then we will talk about, like I said, monitoring. PRV monitoring. So how do you monitor these things to know when they go off, to know how much you're releasing into those emissions concerns, etc. And then we'll go over tank products. So that's specifically covering storage tanks, the high pressure or low pressure storage tanks that you see out, and the different type of tank protection equipment that is on those. And then Q&A. But like I said, feel free to interject anytime you have questions. I'll ask if you have any questions as we go. So define exactly what is overpressure protection. It's defined here, right? So overpressure protection is it's any method of discharging the fluid from your system to atmosphere. You'll just release it, or you may be discharging it into some other kind of system, like a vapor recovery system or flare. But you're doing that so that the pressure in your system is not going to exceed a maximum specified safe value, right? So every system has this pressure, design pressure that they're rated up to. So think of an example, think of a pressure cooker, right? So the old school ones, not the new ones that you just plug in and do it, but those things are basically your vessel or your pressure system, right? So we think of those like the ones you put on your stove top or over a fire. It's basically a pot, right, with a lid, and you can seal it so that you can cook your food under pressure. Essentially, you want to accelerate that cooking time, right? So you cook it under high pressure. And those, that vessel, or that's your system, we're going to say. So on the lid of the pressure cooker, there's a little valve. It's a pressure relief valve. And essentially what that does is just what it is. It's when your pressure in your system or your pressure cooker exceeds that value, or whatever that valve is set at. And the valve is set at some pressure, a maximum pressure that you don't want to exceed, right? So that will relieve pressure. You've all seen that, I'm sure, and see the little steam coming out of the pressure cooker. So that's basically what it is, right? So we're protecting that system or our pot from an overpressure event. And when we think, really catastrophic overpressure events, we think of an explosion, something, right? So, we want to protect our system, make sure it doesn't overpressurize, cause an explosion. We want to protect it. We don't want to ruin our dinner for that night, right, if it explodes. But you're also protecting, your property. You're cooking in your kitchen. You don't want to blow up your stove or mess up your kitchen, right? And then more importantly, personnel, like your family in the area or yourself, you don't want to cause any injury. So pressure relief valves, they are the last line of defense when we're talking about catastrophic overpressure events. All of the fail safes in your process, whatever it is, like your pressure cooker, for instance, you're not over there turning the heat down and fine or something. That pressure relief valve is the last line of defense to make sure that your system is safe and protected, right? And they're on all types of systems. My example of a pressure cooker, that's a little vessel, right? Could be on fired vessels like a boiler, steam generating boilers. Could be on pressure vessels or tanks. Like my previous role, I was worked in the LPG and propane industry. Any huge propane tanks down to little 20-pound cylinders that go onto your grill, they have a pressure relief valve on them. Piping, lots of different applications. So, like I mentioned, there are safety devices. It's heavily regulated because they're protecting, like I mentioned, personnel and property as well. So there's a lot of codes and regulations around these things, how they should be built, designed, tested. But two of the main organizations are the American Society of Mechanical Engineers, ASME, and then the American Petroleum Institute, API. But we'll talk about their role in providing these guidelines. So, like I mentioned, last line of defense, right? They're going to protect you against those critical overpressure, catastrophic overpressure events that ultimately to something going boom, right? An explosion. Like I mentioned, safety devices that need to meet very stringent rules and regulations. And that's all to prevent incidents like what we see here in these 4 pictures. These are a picture of the same facility. Obviously, there was an overpressure event that caused an explosion. And essentially what happened after investigation, they discovered that pressure relief valves were not adequately maintained. They had no preventative maintenance schedule. There's a lack of training at the facility. So they were not maintained properly, kind of neglected in place. And so investigation found out that the pressure relief valves are essentially, they're impermissibly blocked in the outlet. So there was scale and debris that prevented these valves from being able to open. So they were not able to perform when they needed to, right? So of course, we had an emergency at this plant. Happened when most emergencies do in the middle of the night. So the pumps go down at the plant due to a power failure. Okay, power failure, pumps go down. They're not able to move the slurry around to the different tanks at the processing facility. But the boiler is still sending high pressure steam into the process. So without able to move that slurry around, they overpressured at the digester area. And with the PRVs unable to perform because they were blocked, led to this incident. So there's up to like 30 people injured here. Unfortunately, there were no fatalities, but you can see the damage that this could cause or caused. And this all could have been prevented if they had properly maintained, inspected, and done any repairs that they needed to do on the pressure relief devices. The most common type of pressure relief devices are just mechanical devices. So they're self-operated. They don't need any additional input, like for an actuator, with air or electricity in order for these to operate. The most common type are self-operated. So they don't need any external input, but that also means, they don't need to be connected. So you don't necessarily have a good indication of how often your pressure relief valves are opening, if there's leakage, et cetera. That may not be something that you're able to capture. So we'll talk about some solutions for monitoring, like I mentioned, but just keep that in mind. And, keep stressing the importance, and we'll talk a lot about these are safety products protecting ourselves, our people, our property, right? So you'll find them across anything that is creating any pressure, which is most processes in a facility like chemical plants, refineries, natural gas or gas facilities, et cetera. And they're on all these different processes, right? Like storage tanks, like I mentioned, catalysts, fluidized catalyst crackers, coker units, the water treatment systems. They all have pressure that they need to manage, right? So these valves are there. Just one thing to note, though, they are, pressure relief valves, like I mentioned, they're discharging fluid potentially into the atmosphere. They're not connected to a closed header system or something. So they are a compromise between safety, which is what they're there for, right, and then emissions. So, their intent is to emit or release the fluid, which can also be a concern. So, but they're there for safety. They can't be bypassed. They're required to be there just to be able to make sure your process is safe and protected. And they're on all kinds of applications, like I mentioned, all those processes. They could have compressor stations, pumping stations. Like a previous role, they could have pressurized vessels, right, like a propane ammonia tank at the facility. Heat exchangers, boilers, piping, like I mentioned, all different types of applications, and they could be something very mild application where it's not corrosive or very corrosive ones, right? So there's all different types of variability in the options and designs for materials and construction, different sizes, configurations on these. They're pretty much almost all customized for application. Okay. Yes.
Do you ever have a situation where it would be more hazardous to have the pressure relief valve open or break and have the stuff emitted? Would it be doing it? Do you ever have a situation where it would be more hazardous to emit it than to keep it hidden to cause explosion?
No, I think most time you want to prevent that. So if you want to, so you don't want to emit it, you put it into a closed system where you can either retrain that or take it out to a flare destruction and destroy that.
Yeah.
Your process. That's a good question. Any other questions? So I mentioned the ASME. They govern all the information that's in your boiler and pressure vessel code, which talks about the design, fabrication, testing for these different types of processes and their purposes, like pressure relief valves. So how they kind of give you guidance on all of that. And they have different sections depending on what kind of application we're looking at for pressure relief device, or just in general for a construction codes. So section 1 covers power boilers, or kind of what we refer to as a fired pressure vessel. So that's where the pressure comes from a flame impinging on your system, heating it up and creating pressure. So that provides the guidance for safety valves and safety relief valves applications. And then ASME section 4, that's low pressure steam, hot water, low temperature type boilers. Section 8 is a big one that covers pretty much every kind of other pressure vessel, right? So it's non-fired pressure vessels where pressure inside it doesn't come from from a flame impinging on your system, but from like a pump or a compressor, thermal expansion, et cetera. So this is a big one, comes with a lot of different applications. We'll talk about it today. And then section 13, it kind of takes all of the overpressure protection rules from these different sections and just consolidates them to this new section that was created in January of 2021. So, this section has all the rules from different sections consolidated here, but it also references the other ones for some additional information. Okay, and so ASME, they provide all the construction codes, how they're designed, et cetera, but they don't really provide any guidance on, what are the causes of overpressure scenarios, or how do you size a pressure relief valve for an application, or how do you install or inspect or maintain them. So API provides that guidance with these standards and recommended practices. So we have here, like, for instance, this is just a sampling of some of the major ones related to pressure relief valves. We have like 521 that covers, causes of different overpressure scenarios, relieving rates, designs of systems. We have 520, which is split into two parts. That covers sizing and selection in part one. Part two covers the installation. So best recommended practices, for where these are located, positioning of the pressure relief device. And then standard 510 and recommended practice 576 cover, the actual maintenance, how often you should do the maintenance, recommended inspection, repair, guidance on that as well. But so ASME, or the APA, they don't actually do the certification for, any new valve design, or it's actually the National Board of Boiler and Pressure Vessel Inspectors that they provide the guidance, or I'm sorry, they provide the certifications to approve a specific pressure relief device. And they also certify, assembly shops or repair shops that work on the pressure relief valves. So they go out, ASME writes the actual code. API provides like a guidance on how you install or inspect or maintain devices, things. And then the national board goes out and actually does the certification for products, and also, like I said, for the facilities that do repair, maintenance, or even the factories that make it. Okay. And they have to be recertified every 6 years, I believe, in order to keep that certification, right? So I've talked a lot about coded valves, ASME stamp valves, but what are the benefits of having an ASME stamp valve? There's, I've done the presentation a few times where people have said, well, why do I need the ASME coded valve? Well, my application doesn't really require it. So, what are the benefits of it? So we'll talk about that here. Like I mentioned, there's, in order to meet the code requirements, they need to be certified. So first of all, they need to be built in a national board certified flow lab. So they have to prove that their flow lab can test a device and meet all the requirements, right? And one of the big things are the PRV capacities. So we'll talk a lot about capacities today. Capacity, when we're talking pressure relief device, is how much that valve can flow. Okay, so we want to ensure that valve, exactly what that valve flows, because we want to be able to protect our system. And you're going to need to flow a certain amount through your valve in order to relieve a certain amount for the worst case scenario of an overpressure event through your system, right? So, this capacities are very critical for these devices. So determining those, these are all actually flow tested in the lab, like I mentioned. So those capacities are all verified. It's not, if it's not an ASME valve, it doesn't necessarily need to be, the capacity doesn't need to be verified to this extent, the theoretically derived right with equations. But to know that your capacities are certified by an agency, and those capacities on your valve, you can be guaranteed it's going to flow what it says. So, there's extensive testing that's required for, let's say, a new valve design. Like I mentioned, these can be applications or, a product family that has a lot of variability, right? Lots of different materials, the construction, inlet sizes, orifice sizes, across a different, set pressure range. So we do kind of the most stringent one on pretty much all the valves that we create, because like I mentioned, they're almost all custom. So it's like kind of a 9-valve test. We do 3 sets of valves with 9 different valves, so 3 sets of them, 3 different sizes, and across all different set pressure ranges. And they derive a flow coefficient from doing all the tests. So the coefficient of all 9 of those valves across that whole range, they need to fall within a 5% average or range in order to pass the test. And if any of those values do not fall within that range, then they are required to retest, throw out the valve and do a whole new test. So very important. We'll talk about more on capacities, but they're critical to safely protect your system to make sure that you are able to flow that full capacity. And just another note, once the testing is completed, that flow coefficient that is derived from that testing, their ASME puts on another safety factor for sizing, and they derate your flow coefficient by 10%. So it's just an additional safety factor that's inherent in there with ASME after they derate. Okay. Also benefits of an ASME stamp. There's like I mentioned, very tight, very stringent regulations on materials that are used. The set pressure has to be in a tolerance of plus or minus 3%. But you're going to get all of the material reports, CMTRs on any of the pressure containing components for it with every ASME stamp valve. You'll get hydrostatic testing reports, and they're all stamped with a serial number for traceability, right? Traceability is a big thing. So you want to know, how many times this valve has been repaired, where it's been repaired, where it's been assembled. But you'll be able to see all that from, the serial number. And they also have a wire seal that's tied to all the adjustments, so that you can help prevent any accidental tampering with the set points, etc. After it gets in the field. Okay. Any questions on that before? I'm going to move into some specific pressure relief device designs and talk about direct spring pressure relief valves. Unless you have any questions on the requirements. Okay. So I'm going to talk on specifically direct spring. This is the most common type of pressure relief device, right? So these operate essentially like the name applies. There's a spring in the valve, and that spring is adjustable. So you can adjust the compression to adjust the force that it applies down, and that's how you adjust the set point for the valve, the set pressure, right? So that spring has a constant downward force inserted on the seat. So if we take a look at our little cartoon schematic over here, we got, I'll start here at the top. So we have a top, so like a top hat, so what we call the bonnet area for a direct spring valve, which is right here. And so you have these little blue dots here. This is a cross section of the valve, just like this. We have our spring. It's contained in these retained spring washers, and you have an adjustment bolt here, right? So that's applying a force directly down as you compress the spring with that adjustment bolt. It provides different varying force onto the stem, goes through this guide that's sandwiched in between the bonnet, and this is what we call the body, bottom part. And so this is holding these orange rectangles here, which this is what we call the disc. So the disc is what seals the nozzle or the process inside this area. So everything around here is our system process, right? It's coming up here. Let's say this is a propane tank. So I keep using propane as an example. Let's say it's right here. This is all your propane being contained in here. And this disc is holding that down, right? Now that disc could be a varying material. It could be metal, could be an elastomer, could be plastic. But essentially, right, that holds that down until this force or this pressure in the system accumulates, keeps increasing, overcomes the set point of it, which is the spring force. And then this begins to lift off, compressing that spring, and then the flow goes out. Very simple, right? So like, how much more complicated can it get? Well, it will get a little bit more complicated. So we'll talk about some of the different requirements and how this valve can beat those, okay? So one thing to note, when I was talking about capacities or how much the valve can flow, what really controls that in this type of valve is that, like I mentioned, that lift. So how much that is lifting off of this nozzle determines how much flow you get. Obviously, the more you lift off of it, the more flow. And as soon as this gets all the way to the top, which is what we call full lift, that's where we call, that's the capacity of your valve. That's the maximum flow rate. Okay, so you gotta keep that in mind because we'll talk about that phenomenon here as well. But look at this chart here in the middle. We got there's three sections. We have the pressure inside of our vessel, and this is the pressure vessel requirements itself. So we'll start here in the middle. We have the MAWP, known as maximum allowable working pressure, right? Some you may call it maximum allowable operating pressure, etc. But it's essentially, the maximum pressure that we want our system to work up to. But there's an allowable accumulation of your vessel that it's about to go above that. And you'll notice here maximum operating pressure, right? It's below our maximum allowable working pressure because we want to make sure we're operating underneath that, right? We don't want to be operating too close to that because you could get some pressure trips, right? Or your valve may pop off more frequently than you want. So then we look over here on the other side, the characteristics of PRV. We have the set pressure. If you notice, that is pretty much set right there at your MAWP, and that's typically where these systems will be set. And then we have a maximum overpressure, kind of tied in with the maximum accumulation. So we'll learn about this, but there's requirements for how much you can go above your maximum allowable working pressure, depending on your application. So we'll talk about that, but in this case, it's what, 10%, right? 10% of maximum allowable overpressure, and that's where you get your maximum relieving pressure. And then on the bottom side, you see a couple other terms like here's simmer. It's right below so this range right below the set pressure is what we call simmer, and that's essentially when your valve just begins to crack open, right? And it's not really flowing. It's just you have an audible indication that your valve is about to pop. We call that simmer. And then this other range below set pressure is what we call blow down. So you'll see that goes to the reseat pressure. So you'll notice an important factor to notice because you'll see that your valve does not reclose when you get back to your set pressure, right? It takes some what we call under pressure or percentage underneath your set pressure for that valve to fully reseat. Okay, so we'll talk about that. There's some adjustability in that, depending on the valve design. And then seat leakage test pressure. We'll talk about that, but that's essentially, the valve leaking, depending on where your system pressure is. So right here, it's showing that like 90 or 10% under your set pressure, this valve will start leaking. And then you notice the maximum operating pressure is right there. Could be lower, but you don't want your operating pressure anywhere where your pressure relief valves may start leaking, right? Because then you can have issues there as well, right? So usually those are tied together as well. And then we'll talk about seat leakage, like I said, but seating force is kind of, the force of that spring down, which causes the force, containing all of that pressure in there. So that seating force is here on the y-axis as a percentage. So 100% of your seating force, and then set pressure as a percentage on the x-axis. So what we're showing here is our seating force for a direct spring valve, okay? As we know, so as I mentioned here, you have an accumulation or you have pressure building up, right? So as that pressure begins to accumulate and start to keep acting on the bottom of this disc, it's wanting to drive that disc up. And when you're driving that disc up, or you're trying to go against that spring force, you're reducing the seating force, right, on this type of valve. So as you get closer to your set point, your seating force is reduced until you hit your set point, and then it opens. Okay, very simple concept, but just we'll talk about this descending slope. It changes per valve design. So it depends on what kind of valve design you want. And that could, affect your process. Maybe you want to go to a different valve design depending on, your requirements. So, like here, overpressure, like I said, in this example, 10% over your set pressure, your valve needs to maintain or to achieve 100% lift. So this thing needs to be all the way up at this point when you reach your maximum overpressure requirement. Okay. So let's talk about all those things I just mentioned and how this valve can actually achieve that. So we'll get into, this is just a really zoomed in schematic of what we were seeing earlier. Here's our nozzle to our system, we call it, or the inlet, right, from our system. So there's our system down here. All of that is, all of our process is contained until the nozzle, until it hits the disc or what's sealing everything in the valve, right? And then we have an adjustable spring here. It's applying a force down. That's maintaining that seat tightness, seat force. So let's look at it's a force balance, right? We have a force acting up and one coming down. So got some formulas here. We have a simple force balance. It's just the force is equal to pressure times area, right? So in this case, we're talking system pressure times the area of the disc. When I say that, all this pressure is acting upon this area right here. So you just need to figure out what that area is at the nozzle outlet, and then your pressure, and you got the force acting on it. And then that force counteracting it, right, is the force of the spring. A little different, you have a spring, so there's a spring coefficient or spring rate. Constant rate is K. That depends on which kind of spring you use, how many coils it has, how thick the coils are, etc. But that's measured in this case in pound force per inch. And then X is the compression. How much are you compressing that spring? As we mentioned, we can compress it more and get more seating force, increase our set point, or adjust it, back it off, and reduce that set point. So yeah, that's the math that we have for today. But if we look at all the math and kind of think about it, it's pretty simple equations. But like I just mentioned, so we need this valve to lift all the way up, right? By a maximum of, let's say, 10%, the other slide that I just had. So we look at all these forces. Let's look at the force of the spring. We need this valve to lift. But what is happening when we begin to lift this disc off of this nozzle? What happens to the spring? Yeah, you're compressing, right? So if you look at the equation, as we lift it, we're actually increasing the force of the spring down, right? So how do we overcome that? This pressure is going to be what it is, right? It's your system. But you're going to need, that's why you need the allowable overpressure accumulation to achieve full lift, okay, from your set pressure. So how do we do that? So we got an example here. We have, like, let's say this is our nozzle. My fancy little umbrella here. This is the stem and the disc right here, and it's right on top of your nozzle, holding it down. All that pressure is only acting under this small area, right? But we notice here we have kind of like a skirt area for this. This is what we would call the disc holder. So if we look here, it's this red piece. The disc is actually inside of there, and that's what's seated on the nozzle, right? But you notice that kind of creates, like, just like this umbrella. It creates a larger kind of like bell-shaped area underneath it, right? So we all know with an umbrella, when you have flow or there's wind coming, and you can feel that pull up, right? It's the same concept here. We have a skirt area that as soon as this valve begins to open, you start flowing out of this nozzle. You start acting upon a larger area. And as we increase that area, we're increasing that force too, which helps achieve lift. Okay. And then we'll add to that another design element that kind of helps with adjusting some of those characteristics, like I said, like blow down, right? So this is called a blow down ring, and it's essentially just that. It's the ring that goes around the nozzle. this purple thing right here. So that's adjustable. You can lower or raise that blow down ring. And when you lower or raise it, well, I'm sorry. First, that blow down ring, if you notice, it creates kind of this area, this chamber, is what we call a huddling chamber, right here at the nozzle outlet, right? So that helps concentrate all these forces of the flow coming out to help direct them there to help achieve that lift. So that's adjustable. You can lower or raise this blow down ring, and it affects the characteristics, right? So you lower it, you actually have a larger huddling chamber area. So those forces are all contained in there, but what you'll be doing is those forces are acting on there more aggressively. So you're having more simmer, what that means it's going to begin to crack open a little earlier, right? You're increasing that range when it cracks open. But on the other side, when it recloses, it'll be a shorter blow down. So that range I showed underneath the set pressure, it'll close quick. Why is that important? We'll talk about that later, but essentially, if your valve is still open, you're still emitting stuff. And if you've already met your requirements in the system, you want it to close as soon as possible, right? So maybe in those applications, you would look at the shorter. And then if you raise it, it's interactive. Like I said, if you'll get a longer blow down, but you'll start to crack open a little later, closer to your set point. Okay. Pretty simple concept, right? But probably, like I said, more than you ever wanted to know. This is our same chart. This is for a single ASME Section 8 valve. And we provide these charts. I think Dean will talk. We actually have a engineering handbook that has these charts. But again, we'll look at all those same things. Looking at the vessel pressure here this time. So 100, we'll say this is PSIG. So we have 100. That's our set pressure. The simmer is some range under it, but it's very small, right? So let's say 98 PSI or something. It'll begin to simmer. And then here I was like 93, 7% blowdown is pretty typical for these type of valves. So it will reseed around there. And then 10% over or 110 PSI, that's where you have your limit. Maximum overpressure, that means your valve will fully lift and provide full flow at that time. Okay? Yes.
So is that just for this specific valve, that's a percent? Does it change for different valves?
It changes, it could change depending on the application. Okay, so like section 1 that I mentioned earlier, that's for direct fired vessel and boilers, etc. It's 3%. So this is just charting out the lift capacity, or the lift percentage, which means your capacity, and then your percent of set pressure. So just showing how the valve operates. We go up to 90%, and we're coming closer to set point, just start cracking open, and then boom, it goes in a significant lift as soon as you hit set pressure. Like I mentioned, it doesn't go all the way full open. It requires some additional overpressure. And depending on your application, could be 3 or 10%. But 10% in this case, it's fully open, right? Full lift. And then on the closing side, we go past our set pressure. Like I said, it's 92, 93% to when it finally closes. So this is now so you actually see versus this cartoon schematic, imagine cutaway, which I can show here as well. But here we got our spring, just like I showed in the spring washers. The disc holder, like I mentioned, that's it kind of cut away, and you can see the disc actually underneath it. So yeah, it's actually cut away here, so you can see that disc. You can see the blowdown ring. And you can see that little area I talked about, it's a huddling chamber, kind of right there in between that. So, like it's the serrated edges, you can lower or raise that blowdown ring. This little thing right here locks it in place. And then this is the body, like I just mentioned. Here's the inlet. So all of your, your process is here. It's contained here when the valve is closed. But one thing you'll notice is in this design, this particular one, this is a Crosby J series. This nozzle is it's a full nozzle, so it's a replaceable nozzle. It's not it's a separate piece. So all of your when the valve is closed, all of your wetted surfaces are within this nozzle, so it's not actually in contact with the body of the valve. And you can place that nozzle as needed. And then there's your outlet, is flanged outlet. So seat tightness, like I mentioned, that's an important factor. Like I mentioned earlier, I showed a lot of the things up to 90% is usually when we start looking at more significant seat leakage on these type of valves. So per API 527, that's the seat tightness standard. They got requirements for how much allowable leakage you have on a direct spring valve. So depending on the seat material, because like I mentioned, you can have a metal disc or metal seat that seats on top of the nozzle. And that's going to give you a little more leakage and like a lasting. So you have like a rubber seal that's going to seal better than metal, right? So you notice here, there's more leakage that's allowed on a metal seated valve at 90%, but there's zero leakage on a soft seated valve at 90%. That's allowed. And how that's all tested is kind of here with this arrangement. We have a direct spring valve. We're introducing some pressure here up to 90% of whatever the set is. We block out the outlet, and then we just have this tube running to get how much leakage is coming out at 90%. And that's just done by this bubble count. Just sit there and count the bubbles, depending on your set pressure, and then what orifice you have. Orifice is the opening on your nozzle, right? The outlet. Okay. So yeah, that's the allowable leakage there in this chart. This is all in API 527. But keep in mind, soft seats, you have a better seal. Why is that important? Soft seated technology. It could be, first of all, you could have different types of soft seats, like a plastic, a Teflon seat. Could be an O-ring, like a softer elastomer, NBR, or Buna, et cetera, Viton, et cetera. But, like I mentioned, I showed the typical operating pressures, and, that's going to be somewhere underneath your allowable leakage that you have for your valve design. So with it, with these type of soft seats, our Emerson Greenwood Crosby products are typically bubble tight up to 95%. So what does that mean? It means you're going to be able to operate at a higher pressure, right? Your system, if you have a soft seated valve. So you'll be able to operate higher, more productivity, means more money usually. So that, it's an option, but on the other side, you got to be aware of, the limitations of the soft goods, right? So temperature considerations, chemical compatibility, et cetera, they all need to be taken into account, right? But there's a lot of different types of soft goods that can be used, and they all have different properties to withstand certain chemicals and temperatures. Okay. And then one phenomenon we'll talk about that can really affect the performance of a proper performing PRV is back pressure. Okay. So let's say we have our PRV and it's not just going out the atmosphere necessarily, or it could be, but whatever is, here it's tied into, if there's back pressure coming into the body of the valve, it can negatively affect the operation of it, because what it's doing is providing additional force on the outlet. It's providing pressure up here, and what you're essentially doing is increasing the set point, right? And it's directly proportional to the amount of back pressure that you have. So if you have 100 psi set point and 20 psi back pressure, you just increase your set point to 120. So that could be a problem, right? Your valve's not going to open when you thought it was going to. But yeah, just note that all of that pressure in here, it can build up into the spring chamber and everywhere. There's a hole in the guide that allows it to do that. Okay. So the different types of back pressure, one is built up back pressure, and that occurs when the valve is relieving an open state. And so, you know, it could be, it's just due to the orifice area to the the ratio of the orifice area to the outlet area. Could be configuration of your outlet piping, causing any restrictions of the length of it, or, you know, additional frictional forces that is being relieved. So that all that back pressure could build up back into your pressure relief valve, and essentially come back and it'll increase your set point again, could cause your valve to close, right? So ASM, API standard 520 and ASME, they recommend no more than 10% overpressure for built up back pressure. As you can see, the capacity drops way off when you get past 10, which essentially means your valve is closed because that back pressure is building up and trying to close that valve. Superimposed back pressure is a little different. So this is if you have a enclosed outlet to your PRV going into some other contained system like a header. And that header system could be tied into other PRVs or other pressure sources. And then you could have, you know, some kind of pump or something moving all these hydrocarbons up to and out to atmosphere, or flare, vapor recovery system or something. So all of that can create additional back pressure constantly onto your PRV, right? So how do we counteract that? There's certain designs that we can do to balance a direct spring valve. And one is what's a balanced bellows design. So balanced bellows design is essentially an accordion piece that we're going to place here over kind of on the back of the disc holder, and then it isolates essentially the guide and isolates this whole bonnet area from the pressure that's coming in. Okay, so this kind of what we have right here. It looks like a little accordion piece. Pass this around too. But you can see here this little flange piece. It just connects to the top of this disc holder, and then has a flange piece that goes up against that guide. So this is what isolates the back pressure acting in here to going up into the bottom. So when we do that, now we're isolating this. We need to allow this, you know, this area, this moves up and down. So we can't just block this off. We introduce what we call just a vent. So that vent is now introduced on a balanced bellow design to ensure that this can breathe, so that this valve can actuate, right? So it's one quick way also to identify if your valve is a balanced bellows design, just from looking at it on the outside. So you can see a vent versus conventional unbalanced ones. Well, right? Because if it's not plugged, anything that's coming in the outlet will just shoot up there. You don't want that to be tied into a header. But essentially what it's doing is all of these seating areas, this convolution, the cross-sectional area, and, you know, the back pressure is in there. It's acting against these different convolutions, both up and down, to help provide a balancing effect. And as well, you know, that area is equal to the seating area. Okay, so it provides a balancing effect, so back pressure won't affect the opening of this valve. But bellows, as you can see with that one, it's pretty thin material. They are prone to failure, right? They, you know, high cyclic applications, maybe your PRV is opening unintentionally or something, but you can get failures. And as you saw, if you get a failure, you'll begin to leak up into the bonnet area now, and you have a vent. So you're going to start venting any of that process or anything that's coming into your outlet here, or even when the valve opens, it'll all start coming out there. So that could be a cause for concern for emissions, et cetera. But, you know, you can see the different type of failures here. It could be a catastrophic failure with, you know, the really high cycles, et cetera, or small ruptures, just to do normal operation, or even pinhole type leaks can cause, you know, venting out of that bonnet. And this is an example here, but catastrophic, it's over back pressure. Is back pressured very highly, so you can see that it just deformed that nose. So another solution out there to balance a direct spring valve is with what we call a diaphragm, balanced diaphragm. So essentially what we have is a diaphragm. Now, this is sandwiched in between the bonnet and the guide. And you have an additional adapter here. And we put a soft good here, right? So instead of having a bellows here around the whole disc holder and trying to, this now is isolating the bonnet area from any of back pressure in the body. Excuse me. And any of that back pressure will come up here and it'll act on this diaphragm. Okay, so you see here the effective area of this diaphragm, that surface area that's acting upon the pressure is equal to the area of your seat. So you'll get a balancing effect as that back pressure comes in and acts up there, it'll counteract any of the forces acting down. Okay, this is a newer design. This is the actual diaphragm. That's I don't know. But you know, obviously, just mentioned a lot of failures with bellows. This is a much more, you know, you're gonna have less maintenance cost with this because those bellows can be quite pricey. They're our standards to make the ink and melt. And you know, with a soft good, you're gonna be a better cost position. As well, they provide a longer life than having a bellows. And since it is a soft good, you know, typically if they go in and look at the a bellows and take it apart, they're not going to necessarily replace it because it's high cost, right? But with a diaphragm, it's a simple soft good. We recommend replacing it every time, and that just ensures that your valves will remain balanced in case you have any ruptures, etc. And then we also did, based on our testing, there's a limit to how much back pressure you can have with each design. So like with a bellows, we recommend no more than 60% back pressure, those applications, but we've tested with the diaphragm up to 80% back pressure. So you extend that, and well as the same certification as a bellows type valve. So the national board recognizes it, it's approved and can be certified as well, quoted valve. Okay, and then lastly, to balance kind of a smaller portable pressure relief valves, you know, you can't put a bellows or a diaphragm in, it's just cut too compact. They do it with a spindle. So as you see here, the area of the seat is equal to the area of the spindle seal. So this area of the seat is equal to this area. Back pressure acts upon this to help balance the effect of that acting on the seat itself. Okay. And then, okay, good. So last thing, inlet line loss. So pressure losses going into your PRV is certainly a concern. We want to minimize that. What I mean by that is, let's say we have our system here and we have, you know, some amount of piping or something that goes to our pressure relief valve from our system. Well, there, you know, depending on this design, there could be quite a bit of pressure loss. If you have multiple bends, it's undersized, there's other restrictions in there. And you don't want that to exceed a certain amount because you want to be able to sense what the pressure is in your system. If it's sensing something lower here, it may not open and you want it to, right? So ASME, they recommend no more than 3% inlet line loss in appendix M. But you know, essentially, like I mentioned, because these valves, they're reading the pressure right here, right? Sensing it right under this. So if you're sensing a different pressure up here than what's actually here, then your valve may not operate when you think it will, and it's get up a safety issue. So let's look exactly at why is that happening. So here's an acceptable, right? 3%. Very easy numbers to look at. So we got 100 PSI set point, blowdown of 7%. So 7% under set pressure, at 93 PSI, it's going to close, right? But in this example, we have 3% line. So we're going to lose that 3% of our, as soon as the valve opens, you lose 3%. So, you know, 3%, I'm sorry, the valve, you know, will close at 93. So, but since we have the 3% inlet line loss, you lose that. So you actually will close a little earlier at 96%. So actually meaning your system blowdown is 4%, and that's acceptable, right? Because you're in acceptable range, your valve will still close. It won't close until you've relieved your enough pressure, and then you're good to go. So if you have an example with excessive inlet line loss, like 10%, we have the same parameters here, but now we have a 10% inlet line loss. So when you say 10% inlet line loss, that means essentially when this valve, the pressure in here, it will eventually accumulate to the set point, right? And then as soon as that valve opens though, with that line loss, it's gonna only see 90 PSI because it opened at 100. So what's that gonna do? It's gonna make that valve instantly close because your blowdown, but that valve is gonna reclose at 93, right? So if it's only seeing 90 because you have so much pressure drop here, it's gonna close as soon as it opens. All of that pressure will accumulate again in your inlet piping and it'll open and then it'll close again, right? Because you have too much line loss. So what that does, it's called chatter. That's what we call chatter. And that could be detrimental because think about your banging on the nozzle and the disc over and over, it's going to damage it and eventually leakage, right? And we don't want to prevent that. So there's also other pressure relief device designs that can help eliminate that, and Dean will talk about that as well. So just the summary, most commonly used type of pressure relief device is a direct spring. Lower initial cost typically, especially on the smaller sizes, but when you get to larger ones, they can get quite expensive. But like I mentioned, very wide chemical and temperature compatibility, especially with the metal seated type valve. Soft seats, you have to take in consideration temperature and chemical, and then these are certified valves for S section 1, 3, or 8 applications. And then obviously though with these, like I mentioned, the seat force begins decreasing as you get closer to your set point. So if seat leakage concerns, you can adjust the blowdown or the simmer, but you can adjust one without affecting the other, right? So there's that. Also inlet line losses, like I just mentioned, are a concern. Inline testing can be inaccurate. I didn't talk about testing, but there's other pressure relief devices that can provide more accurate testing. It's a little more difficult to do on a different spring. Okay, any questions? Awesome, thanks. I'm gonna turn it over to Dean, who's gonna go over the next pressure relief device and then safety selective valves. But do we want to take a 5-minute break?
Yeah.
Okay, so 5-minute break and then we get.
Thank you.
Thank you.
Yes. Thanks. Let's get started, right?
Think someone turned the air conditioner on. I'm actually able to breathe now. So
It was hot.
it was hot,
Yeah.
but I feel air moving. I might stand right here the whole time. I don't know.
All right, we'll go ahead and get started back. So in 25 minutes, there's an actual break. So probably take that break and hopefully everybody, will you come back after that 30-minute break. So where Warren left off was, we talked about the basics of, the code and standards, and then we talked about direct spring valves. By far, direct spring valves meet application requirements, so they get installed in the majority of applications. But, they do have limitations. So when you size and you select these valves for the different applications, obviously selecting the valve that gives you the most advantages goes a long way, right? It's a safety device. We want to make sure that we meet the overpressure requirements and ensure that we probably are sufficiently protecting the system itself. So another type of device that meets all the same codes and standards is pilot operating technology. And pilot operating technology does have advantages over direct spring valves. So like Warren said, we actually publish an engineering handbook. So if you just Google Emerson PRV handbook, it pops up in a PDF. And it has everything from terminology to, the codes and standards to the fundamental operation of these valves to sizing and selection. So again, it's just Emerson PRV handbook to do that selection. So we're going to start off with just the basic design of a pilot operated valve. So of course, when you look at this valve, the process is directly opposing spring. And this being a little small 2x3 valve, but when you get into an 8-inch by 10-inch, that valve stands about this tall, weighs about 1,000 pounds, really large, and it's also limited very much on its pressure range. Like an 8x10 can only handle about 300 psi set pressure. When you look at pilot technology, what you do notice is there's not that big bonnet up here with the spring directly opposing, our inlet pressure. So what we're going to do is we're going to utilize the inlet pressure to create our seat tightness, and then we're going to use a pilot, so a separate component to control the set pressure, the reclose, and also the action of the main valve. So what the main valve does for us is that's where we size the orifice area and the flow area to determine how much process we let out of the system to ensure we maintain the system in a safe condition, right? So it's two components. Individually, the pilot is its own component that we can set and test, and we can move that on any size main valve. So overall, like an 8x10 in a pilot operated valve, it only stands about this tall. And you eliminate that entire, structure up top that's directly opposing the force of the system itself. So when you look at the main valve, right, we have a piston in there. That's where our seat is. Typically, it's going to be a soft seat, whether it's an elastomer or plastic, by orifice and by temperature and chemical compatibility, we get into the selection. But the piston itself, is a dynamic moving member in there. It's unbound. So up at the top, we're 30% greater than we are at the nozzle there. So as system pressure comes online, we don't have a lot of force holding that piston down. right? We're gonna actually take the operating pressure and put it on top of the piston. So we can actually do that two ways. One, the most common way is what we call an integral sense. So we're gonna pick the pressure directly at the inlet of the valve. So as your system pressure comes online, we come up, we pick the pressure up, send it into the pilot again, where we're gonna control set, reclose, and the action. We're gonna divert that pressure on top of the piston. We call that the main valve dome. So with that area larger on top of the piston, of course, that pressure times area is creating a downward seat force. So the higher operating pressure that we have, a higher downward seat force we have on the main valve. So the main valve actually becomes tighter the closer you get to set pressure. So word to mention, like you can have this valve in a metal to metal seat. It has a allowable leak rate at 90% of the set point, which means to have no emissions, no product loss, you have to operate below that 90% to give you zero leakage. If you have a soft good in here, you get up to about 95%. So these valves inherently already have those soft goods in there, but also by applying this technology to it and utilizing the area and the pressure to create the force, these valves can get, up to 95 and a little bit higher the closer you get to operating. So again, less emissions, less product loss if you're operating close to the set pressure. So to get this valve to open, the pilot has to do its job. What it has to do is it has to begin to release the pressure up here, which is creating the seat force. And once we, eliminate at least 30% of that dome pressure, now that piston is in an equilibrium state. The inlet pressure is higher by 30% than the dome pressure. So I'm able to move that piston and barely crack it off the seat. Now, the way that we do this is we look at the different types of valves that we have in direct spring valves, and we also use the same terminology for pilot operating valves. So a safety valve is a valve that we use in compressible media. Right at set point, it has very sharp, crisp pop, high gain off of the seat. And we flow a lot of that, process out of there in a very rapid opening. So in a snap action pilot, we're going to call this a safety valve as well. Because what this safety valve does for us, by applying it into a compressible media, at set point, when the pilot opens, it completely evacuates the pressure that was in the dome, creating the seat force. And with no pressure on top of the main valve piston, the inlet pressure at set drives the piston into full lift. So mechanically, you're at full lift at the full flow area right at the set point. Right, so you can take advantage of this, especially depending on the industry that you're in. If you look at an ASME application, on the chart that Warren had, we had maximal allowable working pressure. So the design of the vessel was built to ASME Section 8, and in that, they determined the maximal allowable working pressure. On Section 8, it doesn't really define the set pressure, but it does give you information about set pressure. It actually says that a valve or a pressure relief device can be set as high as MAWP. You can be set anywhere below it, but you can be set as high as MAWP, right? So that tells me that, I can't go above that number. So I'm getting into selection of the valve. But then there's industries like the DOT, like natural gas compressor stations. You can look in the CFR, and they don't really define the set pressure. They don't use a statement like, you can set it as high as. What they say is your valve has to be at full lift by 10% above its set pressure, so 10% overpressure. So a valve that goes into full lift right at set point, it has, nothing more to gain. We're at the full maximum flowing area. So as your system pressure increases from set and then accumulates to 100, 101, 102, 103, all the way up to 110, you're actually able to utilize that and set the valve above what the natural gas industry utilizes the term MAOP, maximum allowable operating pressure. So again, the selection of the valve, the sizing, the industry, the application that you put into it, that you're going to input, it is very important. So the snap action valve, we're going to call that a safety valve. The modulating action valve, we're going to call that a safety relief valve. We talked earlier about PRV, pressure relief valve. That's kind of a real generic term. It kind of covers all of them, doesn't specify balanced or conventional, direct spring or pilot. So pressure relief valve, some plants use like pressure safety valve or PSV tag number, and that's the identifier for that device within a unit, right? So pressure relief valve actually does get broken down into relief, which is going to be for liquid flooded systems, like the discharge side of a pump, like a liquid flooded vessel. It's going to open on liquid, it's going to flow liquid, and it's going to reclose. So that's going to be a relief valve. The safety valve, like I said, when I defined this pop action valve, is going to be a compressible media only valve. We want that valve to really sharp, crisp pop, high gain, release that high energy, compressible media as quickly as possible, and have a controlled flow and a controlled reseal. But a safety relief valve, like a modulating pilot, actually can do both. It can lift gradually on water, it can cycle water, or liquid, and it can close off. It really doesn't matter the media that it's seeing as it opens and cycles and recloses, right? So a safety relief valve gives us some advantages by applying it into applications where we may have a mixed phase application, right? Or just a standardization of that type of pilot. So when you look at the little cartoon that we have up here, remember, this pilot, when it opens, it completely evacuates this pressure. So this piston goes into full lift. So this valve right here is either closed or it's full open. There's no in between. On the modulating pilot, the pilot actually regulates the dome pressure, right? So for the lack of a better way to say this on a safety relief valve is that it works like a back pressure regulator. As you have increased pressure into the pilot above the set point, the pilot reduces the pressure in the dome, which means I have less downward force, but I still have pressure in there. So the inlet pressure actually pushing the piston up against the force still in, or the pressure still in, and it allows that valve to lift in accordance with the demand, right? So instead of popping off of the seat, it could just crack and it could just stay in that position right at set point. But if the accumulation in the system continues to rise, I get a pressure increase into the pilot. The pilot reduces more pressure off of the dome. The inlet pressure at 101, 102, 103%, it just pushes the piston higher and it creates a larger flow rate. So this valve has a nice, smooth, gradual cycle to it, right? You come by our booth, we actually have one out in the demo stand. So you can hear, instead of popping, it'll just go kind of lift up and down and cycle, which is good because a modulating action valve gives you some advantages. One, if you have a lot of accumulation in your vessel and the valve snaps and pops off of the seat, it rapidly reduces that pressure, which means you rapidly lose all that product, whether it's going to atmosphere or tying it into a flare header or whatever it may be. If you have a valve that only lifts in accordance with the demand, then you really minimize the effect of that product coming out of that system, right? You don't have that loss, you don't have that environmental impact. So the main valve being its own component, one, the body is actually part of the flow path. That's where we tie in and put the pitot tube to pick the pressure up. So we have a semi-nozzle in there. Here's our piston again. So over here we have an L shape. That L shape is nothing more than a molded seat. So the reason we have an L shape in there is to give us a larger surface area to capture the seat on, but also a larger surface area to seal off on, push down onto the nozzle. Because typically most valves, like when we make this valve in an elastomer seat, we utilize an O-ring. And of course that O-ring, and by the time we capture it and where we seal off on it, we take about 3/4 of the area of the O-ring. So it sets off on a very, very small area. So by putting this in there, it gives us a lot of stability in the seat, gets us up to much higher pressures, and also a lot of different materials that can be applied in there. When you think about repair on pilot operated valves, it's always about the soft goods. So just in the main valve here, we have a nozzle seal, we have the seat, we have a piston seal, and we have a liner seal. So this valve, if it can be depressurized in the system, you can isolate it from the pressure. You can actually take the cap off, pull the piston, change the soft goods, drop it back down, and you can do a VR right on the system itself, via full VR repair. So one of the things about this piston, you see up on top, there's a bolt, and that lift stop bolt creates how much travel we allow the piston to come off from the nozzle, right? So in this, we got about an inch up top here or so. So when this valve would open, it would travel till the lift stop bolt hit the cap itself. Well, that bolt becomes very important. I'm going to use an example. When you think about the way these direct spring valves are set up, API recognizes in a 4-inch inlet with a 6-inch outlet, they recognize L, M, N, and P orifice size. So L being the smallest, it's like 2.853 square inches. P being the largest in a 4x6, it's 6.38 square inches, right? But each one of those valves are completely different valves. The AV dimensions aren't the same in a 4x6 valve, the nozzle, the seat area, the flow, all that kind of stuff. It's 4 individual valves to meet those 4 orifice sizes. Well, since we control the travel of the piston, what we do in a pilot operated valve is the diameter of the nozzle is set to the largest orifice. So in this case, it would be the P orifice. And then to get to L, M, or N, all we do is adjust the bolt to adjust the travel to change the flow area to get us down to, whatever orifice we need. So if you had a system where you had this valve in there, basically, if you had to derate it, maybe you had an API 510 inspection on it, you're derating that, due to the corrosion or whatever on that vessel, and you're going to lower the pressure on there. All you would have to do here is adjust the flow or adjust the lift to adjust the flow. Here, you basically have to change an entire valve, right? So again, there's just all these different advantages that we can have. So modulating action, I'm actually going to show you the flow path. It's kind of cumbersome, but it shows you how the valve effectively works and modulates in its lift. Snap action pilots have been around since the late 50s. Started out in the oil and gas patch, went out to natural gas. So those combinations of valves have just come through for decades and decades. Modulating action valves actually started, about the late 70s, but really took off in the 80s. And then in the 90s, it actually started to help outsell the snap action style of pilot. So here's an internal of a modulated pilot. So I want you to look at a key component in the middle here. And this is a spool piece right here. So this spool piece has 3 elastomers on it. One is what we call the inlet seat. That means pressure goes into the dome. The middle O-ring is what we call the outlet seat. That means pressure's relieving from the dome out to the pilot exhaust. And down at the bottom, that seal is what we call a balancing seal. So this pilot actually, when it releases the dome pressure, it's exhausting the dome pressure back to the main valve outlet. In other words, we don't have any of the media going out to the atmosphere, right? So we're going to capture that in the dome, but once we reach over pressure, we're going to release that through the pilot. We're going to send that to the main valve outlet. So again, I'm going to walk through the porting up top. So up top right here is going to be our spring. That's controlling our set pressure and our reclose, right? So through porting, we're going to pick the process up. And as we pick the process up, we're going to send it under what we call the cinch chamber, and that's directly opposing the force of the spring. So that's going to be pushing upward on this cinch piston. But that pressure also flows through the porting around the inlet seat, across there, and it goes in, and that's where it loads the dome. Right? So it doesn't matter, again, if it's a gas, vapor, or liquid, that's going to be the flow path. We're going to load the dome, and then we're dead end. So when we're dead end in there, that's the startup, and we've created our downward force on our piston to keep the seat closed. So through a process of reaching, the set point, what has happened is we got the increased pressure under the piston, it pushes upward. So when it pushes upward and compresses the spring, this device closes the inlet seat, and then it pulls up a little bit more, and the spool piece moves off the outlet seat. So now the dome pressure can be released to the outlet. So again, it's kind of hard to see in here, so we're going to go a little bit more cartoonish, right? So that startup, what we have is a valve that does not have a lot of seat force. We need the operating pressure to come up and load to create the main valve seat force. So once the system pressure comes online, comes into the body of the valve, it's picked up. That's where it goes into the cinch chamber, directly under the spring. Through the porting, now we come down and around the inlet seat. Our process will come down and load the dome. That is what the valve looks like under normal operation. Normal operation for a pressure relief valve is closed. It's not supposed to do anything, right? Until you reach some overpressure scenario, until you reach some event that's going to increase your pressure to get the valve to function. So this is what it looks like all the way up to 93% of set pressure. What begins to occur at 93% of set pressure is I have pressure working under the spring here and it starts to push upward. So when it pushes upward, it compresses the spring. What it's doing is it's moving this feedback piston and it's going to close this off. So at 93%, I've closed the inlet seat. Now this is very important because when the main valve is open and we have flow coming out of the main valve, with the inlet seat closed, I have static pressure from the inlet seat back to the pitot tube, which means I have a non-flowing pilot. So the main valve is open, releasing the overpressure from our system, but I do not have a continuous flow path through the pilot that will exhaust out the porting. And that's important because the snap action pilot, it releases the dome pressure directly to atmosphere. So if you have a process that's flammable or toxic or anything like that, you don't want that venting off the atmosphere, right? So non-flowing becomes very, very important. So when we go to 93%, we're in what we call the null position. 93% means the inlet seat is closed and I haven't even opened the outlet seat. So I've trapped pressure between those two seats in my dome. 93%, I have zero leakage out of this valve. No leakage across the seat here, and I don't have anything coming out of there. So for 93 to 95%, this is the position of the valve itself, right? So what begins to occur at 95% operating pressure? We push even more against the spring. We create more lift. And since the inlet seat is already closed, as I create more lift, I pull the spool up and I begin to bleed the pressure off of the dome. So from 95% all the way up to the actual set point, the outlet seat will be in whatever position it needs to be to ensure that I have released that 30%, and that allows that inlet pressure to crack that piston off and lift in accordance with the demand. So again, you can see how it functions like a back pressure regulator, right? I have increased pressure here, which means I'm at set pressure or above set point. So I'm going to have reduced pressure occurred here. And the higher pressure I get at this, the higher pressure I have pulling up, continuing to open the outlet seat, and I would just allow enough pressure to create the flow area needed to maintain the system very close to MAWP. So if you think about every system that has a control valve or a regulator, right? We have an upstream pressure that's much higher, and then we have a lot of equipment downstream that we would have to protect due to overpressure. If that control valve fails in the wide open position, we could send pressure down that could damage equipment. We don't want that to happen. So typically between a control valve and what we're protecting, we're going to put some type of pressure relief valve. If you put a snap action valve, a valve that really pops, and you have a rapid reduction in pressure, the control valve says, wow, something's really using a lot of this. So what does the control valve do? It opens up. It wants to put more pressure where you don't need it because we have an overpressure event occurring. If you have a valve that modulates and only lifts in accordance with the demand, and you release the minimal amount of pressure off of the system, the control valve senses less of a pressure swing. So it creates less of a movement in the control valve to reload that pressure. So you get rid of a lot of the instability and turbulence that can be created by safety valves and control valves. So we're in this modulating action, right? So if the pressure begins to reduce, all that would happen is the spring force would, in the sense chamber, would measure that pressure reduction and it would just start pushing everything back down. At some point, it would reopen, it would close the outlet seat, it would reopen the inlet seat, and it would allow us to do that. So with a modulating action valve, the valve can be anywhere from closed to cracked off to wherever the overpressure takes it. It does not pop off of the seat. Now, if you have a rapid ramp up effect, it opens, it'll reach full open, right? If you get to all the way to 110% overpressure, the pilot will reduce the dome because the full lift actually happens at about 60% total reduction in the dome, right? That will allow the main valve piston to go into full lift. So with that, you get into that very modulating effect. To get this valve to close, we have to reduce the pressure below set. And once we reduce the system pressure below set, the spring force overcomes, pushes back down. It's going to close the outlet seat. It'll reopen the inlet seat, and then our normal operating pressure will reload and close the main valve. So not only do you only lift in accordance with the demand, but when you go to reach your blowdown to where you reseat that, you have minimal in that band. You have the least amount of product to come out of that system. On a valve that snaps or pops, you have full lift rapidly. You begin to lose a lot of pressure. And as you lose that pressure, you get into the blowdown, and that blowdown can be 7 to 10% below. So you have a much wider band, a much more process being exhausted out to get in either the atmosphere or to wherever you've tied in that discharge side to be released. So I'm going to show this video, and then we are going to take our coffee break, right? So I'm going to explain the video real quick. So it's going to be a modulating action valve. We have it on a test stand. It's one that we gradually lifted on water, but just to shorten the video, we've gotten into almost a full lift state, which would be 10% above its set point. So what I want you to do is just kind of listen to the water flowing, because what we're doing is we're maintaining that 10% above the set pressure by pressurizing that liquid filled test vessel with nitrogen. So as the liquid level begins to deplete out of the test stand, the nitrogen now is in the flow path. And as the nitrogen comes through and it goes through the opening in the body of the valve, there's a lot of turbulence created. There's a lot of back pressure built up. Warren talked about the adverse effects that back pressure could have. The key to this video is you never see the valve close off. You never see the valve cycling, because in a direct spring valve, as you build up back pressure here, all of that builds up and it wants to create downward force. So the valves could slam close, open back up, slam close, and go very, very unstable. So again, listen for the water. Listen as we transition to a two-phase, and then we're going to reduce the pressure and get into our closing on a gas tank. So a true safety relief valve. Oh, I just talked about it. Come on. How'd the guy play it? There you go. So we gradually lifted by 10% over full pressure. We're going to have full flow. So we just got water through the maximum lift that we have in the valve. So you can just hear just water flowing through it, right? So your installation, your reaction force, your downstream piping, sizing off a modulating valve versus a full lift valve. You hear a little bit of change going on. Now you have nitrogen. Now think about the turbulence on your downstream header, the body bolt pressure that would be created in a direct spring valve. Now you have this mixed phase. Now you have a very high energy compressible media, as it crosses the nozzle, expanded in the body mold, going out with the water. The reaction force change, everything that's going on in the system itself, it's creating instability, a lot of turbulence on the downstream side. So again, nowhere do we see the valve actually closing. This valve would have a tremendous amount of, instability going on in the valve, because the spring is always pushing down. It's always saying, I need to close, I need to close. And all of this is trying to keep it in a lift state. So that valve will become very unstable and sporadic.
So we're gonna force all of the water out of the test tank. We're gonna get to a gas, reduce the pressure. And just below set point, the valve recloses. Any questions? So hopefully you come back in 30 minutes. Yeah, they'll say, well, we just saw the video. What else we got? Yeah, why don't we take the coffee break? And if y'all come back in, I'll already be in here. We can start whenever, so.
Oh, thank you.
And with a lot of school.
Yeah, it's one of the things, yeah.
And almost exclusively industry experience. Like this makes, and it always seems very opaque.
It really does. I mean, pressure relief is a lot of times the last thing that's thought about. And a lot of time on projects, that's the last thing purchased. Right? Because you go through all those different overpressure scenarios and everything else to design the system. But like I said, that engineering handbook, I'm not sure how many you may have stepped out, but if you just Google like Emerson PRV handbook. So we have a terminology, the fundamentals to code to standard sizing and selection, all in one book. So just Emerson PRV handbook.
I think, awesome.
Yeah. So everything that we talk about here is covered on there. There's, any information, that's available out there and stuff, so.
All right, perfect. Do you have a card or something? You're not gonna be able to stick around for the last session, last part.
Yeah. Where do you located?
Check my gloves.
Here in Texas.
Thanks.
So my counterpart can do handles,
Mine as well.
yeah. Like where are you,
At HQ, side for packaging environmental HQ, side for making sure everybody's in compliance.
okay.
So that's fun.
Yeah.
It's not.
Yeah, they're happy to see you when you come out, right?
Yeah, it's like, I'm the booking man now.
Yeah, I agree.
So, it's like, run.
Yeah.
Check around here.
Can I take a picture of you there?
Sure.
Yeah, so my counterpart who covers Texas since I live in Louisiana and go east is Earl Reshaw. So if you send me something, I might just flip it to him and then you get with him. All right, thanks so much.
Thank you.
Appreciate it.
Take those two babies. You're gonna use after lunch, you already used,
He's already used all that.
and you use the safe selector.
I haven't done it yet, but if you want it, I'll give it to you.
No, it's not something right.
No, because I have the like animation. I don't really need it. That's what I'm saying.
That's okay. Didn't hear. I can take the other one.
Well, it depends on how you.
Sure. I don't know. My presentation makes sense.
Yeah.
Well, was it good? Good questions?
No questions.
No questions.
I don't know. More than you have? I don't remember. Like 4? Yeah. Yeah, there's more questions. Yes.
Both of us still becoming,
No, that's good. That part is true. I mean, honestly, you try to find that one or two faint contact. I think we found 2. It turned out to be. I mean, one was in yesterday. I already forgot the gentleman's name, but that's it along. But he came by the booth as well. And an older gentleman, gray hair. And then today, a girl out in the Permian with an exome. So, she has hatches that are corroding. And, so when she flips, OAE valve, he's gonna get more in it. I'm sure Vincent just knows this person money, Emerson. So I mean, those are real contacts to get information to.
You know, the lady, I put it on the file, I went to the book for the.
Yeah, I saw her. Yeah.
She's. What's the name? Actually. She was over five miles. Yeah, it's just pretty. It was like off the marathon. It became very important.
Yeah.
Just really, just you got a different kind. If this guy sitting down, they have a major. Their septic green.
Well, they got one too, but
I'm 18. Septic cheese. I mean, we normally don't process people. It's the only place.
it's like he said, he's in HQ. You can't find these people at plants. It's difficult to go to plant levels and find someone that has it as a full-time job.
Whether they, and it's what for political size.
I mean, they're not even part of like the EHS group, so
Very interesting.
yeah, we'll see if we even have an issue.
Yeah.
That's good. Or what would be weird is people think that it was 2 hours and 2 hours.
Something 2 hours.
It's the same thing.
Yeah.
Yeah.
Mind blowing. Exactly.
What's that? Stay here.
Yeah. Guess they're not serious about the coffee and the coffee break. There's no coffee.
Oh, really?
Yeah. It's kind of coffee break.
You haven't been?
Do you like field? Yeah. Thanks. Yeah, I feel better than yesterday. Sure. Yesterday was a struggle. Hey, Dean, this is the, now I'm gonna sell this. This is what you're talking about.
Yeah, so again, that's kind of clunky the way they did this. That's an old way we used to do it. Now, it'd just be like a T, yeah. And like having a big T, but yeah, so this shows vent to atmosphere. But tying it into the main valve outlet, again, sends it off somewhere where it's not right next to the person. Okay, so that's that. There should be on the next page, so this right here is, our remote government capability. So it's a valve tied into the same tubing Back to the dome. If you can just,
That's what's sold in there.
that's right, yep. You just trip the valve from wherever, which means you pop it.
Right.
So,
I lived in all-
yes, so remember the pilot gets tested on its own pilot screen.
Okay,
So we just call it MT. And so what they do at Stanford is when the pilot's put together, they test it and they seal it on that drum chain, right? So once it's sealed, then it moves on down the line where they're putting together the main valve, putting the accessories and tubing together. That just becomes now part of that assembly line.
okay, thanks. Yeah, I'm gonna send you.
Yeah, so all kinds of options to move the piston. It's just not easy modulating versus a snap action for sure.
Did you see any coffee up there? Yeah.
Nope.
I mean, yesterday too, they get conflict with 3 minutes and they threw
They
away.
took it away. And I was at a different hotel. I mean,
I mean, they call us a coffee. But there's no coffee.
He probably had to put pay your. Oh, you won't. But you know, like that, yeah, we can't have fun.
Okay. Do we test valves anything higher than 10% molten pressure? Can we do up to 21% fire cave? Steel.
so even though those accumulation values change,
Yeah,
nothing changes in the valve. We know that the valve's at full lift at 10%.
yes.
So we don't we don't have to bring it up. We can just, extrapolate out based off the percentage with the valve already at full flow in its flow area.
Yeah.
And the coefficient.
Okay.
So now, do we have the capability? Absolutely. At El Campo, depending on the set pressure, they could bring it up to 20.
Right, but we don't need this.
We don't need to.
Well, we can calculate.
Yeah,
Okay.
Yeah.
Thanks.
The question of the guy yesterday was not a very question. Remember? Daughter, you said it again, never heard me.
Oh, he was talking
Was it?
about the combustion
Yeah, over with the,
release of methane.
yeah.
And I think he's talking about like, yeah, BTU.
yeah, that's real specific
Yeah.
to the process and not the valve. So
Right, it's more on his end.
I thought he was talking about how fast the valve's gonna burn. That doesn't make any sense, but
no,
that's a weird question, but.
I mean, I've been asked about, what is that, the boiling liquid, boiling liquid.
Yeah, levy, yeah.
So because the relief valve just opens and flows. But if the tank or the vessel's still on fire and all of that liquidy, as the liquid begins to reduce, it's more walls exposed to the fire that's increasing the temperature, which means at a higher pressure. The valve could actually be wide open and flowing, but the tank could still boom. And yeah, because you get down to, you lose all the cooling effect of the liquid that's inside the vessel, and now you have nothing but vapor inside the vessel, and you have all that heat input.
Yeah,
Yeah, so
yeah, that was a big thing.
but again, I was asked that, like, well, how does your relief valve handle that? Well, the relief valve was open and flowing. That's all it can do, and that's what it's there for. So that case is above and beyond. They got about 10 people next door.
More regulation. Regulation.
Yeah,
Yeah, no trouble. People on this type of.
event. Yeah, exactly.
That's
Well, it's 5 minutes after 3
What time? 3?
Oh, no one's back.
and no one's back. Oh, wait, it actually says 3:15.
It should be 3:50.
Okay, okay. I still think, I still think splitting it with his coffee break,
Yeah.
is gonna be tough to overcome.
45 minute break.
Yeah,
So.
Oh, and they don't give us the time back?
Exactly. So that we're gonna have to compress a lot of material. So make it up.
Maybe skip the safety splinter out.
well, again, that might be something that we have to do. And if,
Or just overview.
but I wonder, again, it'd be interesting if new people come in thinking it's a repeat.
Yeah, they were saying to new people, oh. They will get that.
Cause it doesn't say so. It just
It
says,
doesn't say PRV safe city continue.
It says it's an independent train.
And that could have been, these people thought this was.
2-hour one. Exactly.
Yeah.
You know, I mean, they make their own plans. And plan. Okay.
I mean, so are we prepared if we start over? What if new folks come in? Do we ask them or what?
But if the old folks are here, then it's kind of.
Then it's redundant.
Yeah.
Absolutely.
They're wasting their time, right?
Yeah. That's crazy setup.
Yeah, it should have said continuation or something.
the last thing on that. That one TV 1, 2, 3 option. That little thing. Is that? Price that in anything or? Do they have to put it back?
Yeah, I think they gotta get that from the factory. Yeah. I don't think we ever put it in the price book.
You are?
You guys leave there?
All right.
Break a leg, okay?
Yeah.
One, right? One or.
Yeah, well, where's yours? Well, that's on the other side.
So the, okay to take this one, right?
Yeah, yeah.
So you're
So is Marcio,
Marcia's gonna be there with me.
so what time do y'all get done? 4 o'clock?
Yeah. So we flip the presentations, so they're gonna thank after you.
Oh, I see.
All the monitoring them.
Yeah, cause those guys should be finished up.
Yeah, yeah. Kind of frantic thing.
Yeah, this whole conference is. This is the most unorganized conference I've ever been.
Hey,
2 hotels.
Yeah.
I mean,
coffee.
yeah, I gotta be honest, Warren, when Marcio walked up yesterday with beer, I was fucking pissed. You couldn't have been here an hour before to knock this out and get out and tell us what you wanted. Yeah. Oh, he looked at his phone and said, oh yeah, I got a lot of missed calls.
Yeah, I done it. Got it loud.
I mean, come on, dude. I mean, this is your gig. This is, you know, you set this up, you had the, but I don't know if, no. I mean, I met him at Exchange, but that was it. I know one thing, if Brett asked me about it, I'm gonna say it was a waste of time for us.
Close thing.
If he tells me one more time, I can go to some room and get food and drink. Is that all you're worried about, dude? I mean, are you talking to any customer? Yeah.
And so I wanted to go home. So as soon as you left, we left, right? I was
Yeah.
going to, yeah. We're walking out, going back. And then he's like, no, come just with me back. And I was like, okay, so we all started walking. He's like, we're gonna go the long way so I can show you 6 feet and all this. And I was like, we were already walking and I was like, dude, are you kidding?
Are you serious?
Walking, I was like, It's like, when you come to Austin, like, all.
Yeah, I mean, hey, I don't mind doing,
He's more on the social part.
right. I mean, if you want to do a boondoggle, that's fine out there, but this is just as unorganized as it is. I mean, setting that thing up though, when he come walking up a fucking hour after we got there.
Yeah.
Oh, well, let's put it together. I was about to say, you're right. You are putting it together because I'm fucking leaving.
Okay, I don't know.
No. And then after I stood there for like 15 minutes doing absolutely nothing, I said, I'm leaving there. Why am I doing? He's playing around with his computer or whatever. Yeah, well, Marcelo, the one I heard, where you going? I said, I'm leaving. Yeah, I said, I'm leaving. I waved at him, dude. Too many damn men standing around here. Exactly.
Oh, you have to give me that 1 minute.
Sure enough. And I've seen like, I don't know. If no one shows up, obviously we're playing, but I've seen 25 people walk by and none of them have looked at this room. Dude.
Yeah, I definitely don't think we need to do this.
Oh,
Maybe the smaller breakout session.
yeah, pick one and I would title it more around exactly. Talk about seat tightness
Yeah.
and shit like that, but yeah, all of this, I don't know. Yeah, so like that selector about Marcio said, man, last year, the guy who runs 4C said the selector valve's awesome. And I'm looking at him like, does he buy shit? It sounds like he runs the 4C thing.
Right. It's good.
Yeah.
Yeah. That guy shouldn't do that. You had 10 people? Yeah. Just about, yeah.
No, when I walked in, there was 10 in there.
Yeah.
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 Well, guess what?
We're done? You know what we said is, you know, the way the schedule's written.
The way the schedule's written, it looks like it's two-hour sessions.
It doesn't say that.
It doesn't say part one, part two, does it?
Did we do that?
It doesn't say continued part 1, part 2
Yeah,
or
it does
anything.
not say anything.
So, you know, the people that came in.
Well, why would you
Maybe they
have
thought this was a 2-hour thing. But it's just, yeah, no, leave.
Well, why would you have a 45-minute?
I'll be right back.
Well, that was another thing. And by the way, yeah, everything's worked perfect.
You can have like, 5 or 6, 5 to 15-minute breaks rather than having one fast 45-minute break at the middle. No one's gonna.
And the 45-minute break cuts into your actual time. So again, they didn't look at our 4-hour time. They look at I think they really thought this was two individual.
Yeah, they cut out 45 minutes.
No, I mean, there were like 6 people's names for 2 hours. I guess.
I don't know. So did you get any good feedback? Any discussions after?
You
That's
told
good.
us to stop by the booth. We said we have everything set up. You can come see
That's-
cowboy hat.
Yeah.
Because I feel that was the most relevant presentation to the booth.
Oh, yeah,
It's
yeah,
like
absolutely.
right there,
Right.
So,
Yeah.
But some of them, a lot of them did agree that, yeah, the issues and stuff like that. So we'll see.
Yeah. So when I walked in on your part, you were finishing up with the end and you were pointing out the stuff and the guy in the front, he was just taking notes, shaking his head, yes, shaking his head. The gray headed guy up front here
Yeah.
and writing it all down. And I was
That was
like,
Jim.
no, he was on the other side. This guy on this side of the room.
Oh, this side of the room?
Yeah,
Oh,
yeah,
okay,
yeah.
okay,
I stood
okay.
right behind him.
Okay.
Yeah, Jim was over.
Yeah. Yeah, I mean, no, they like took it all in, but that's it. Hopefully something comes out of it.
This is the, I feel the most relevant.
For this whole conference.
Yeah, this whole conference.
That's what Warren and I were just talking about. I mean, one, the way this is worded, just PRV University. It's not good for this conference. I mean, you would really have to put something
fundamentals of PRV or something like that.
Yeah, but you also throw in seat tightness to eliminate emissions. and Whatever you can.
Something attractive to compare.
Absolutely. Yeah. But yeah, the 5 people we had, they, as soon as we got to the coffee break, they packed their shit up. They're like, thanks, see ya. Even the guy from CP Chem, I mean, he was like, well, I gotta go. Oh, okay.
Oh, shit.
They're not gonna like some of the things. How do I stop recording?
That would be right at 1, right? So we got over 16 minutes.
Oh, yeah, yeah,
Yeah, so that's this whole session. Right?
yeah.